Hello and welcome back. In this lecture, we're going to talk about the Kullback-Leibler divergence, or KL divergence for short. So the KL divergence measures how two probability distributions Px and Qx are different. So let's say we have two probability distributions. The first one is called Px and it's the green one, and the second one is called Qx and it's the red one. Now what we want to do is measure how these two distributions are similar from each other. So what we want to do is use the KL divergence to measure the similarity. So basically, KL divergence gives a high value when the two distributions are different, and it gives a low value when the two distributions are similar. Now, when does it give a value of 0? If the two distributions are equal. So what does it mean to have a loss of 0? Again, that means the two distributions are similar. And what is the neural network's objective? Is to make the loss 0. Therefore, what the KL divergence does is that it tries to make two distributions similar to each other. So it might make the Px, which is the green distribution, similar to Qx, which is the red distribution, or it might make the Qx similar to Px, depending on what you want and how you place each distribution in the equation. Okay? So basically, the loss is high when the two distributions are dissimilar, and the loss is low when the two distributions are similar. So let's have a look at a small example. Let's say that we want to estimate the probability distribution P, which is this image right here. This is this distribution. We want to estimate that with a normal distribution Q. Okay, so this is the normal distribution, which is the blue shaded area right here, and we want to estimate P with Q. So this is one example of KL divergence. Another example, if you just switch between P and Q in the equation that we're going to see later on, then basically what we're doing is using the probability distribution P to approximate the normal distribution Q. Okay? So that's an example of the KL divergence. So let's have a look at the equation. Now basically it's the difference between the entropy and the cross entropy loss. So we're going to take our cross entropy loss and we're going to subtract the entropy from it. Okay, so it's the difference between the cross entropy and the entropy. If you're looking at the equation in this way, then it's cross entropy minus entropy. And if you look at it from this side, then it's basically the entropy minus the cross entropy. So both of these equations are exactly similar to each other. Because if you look at the logarithm properties, then log of a fraction, so for example log m over n equals to log m minus log n. So if you take log 1 over y, yi, which is your predicted value, and you apply this property to it, then you'll just get this equation right here. So it's exactly the same thing. So it's the difference between the entropy and the cross entropy, or the cross entropy and the entropy, as we said just now. So basically, if you apply the logarithm properties and do some arrangement to the equation, you'll end up with this right here. Okay? And basically, if you take this, so remember, log a fraction is going to be equals to log the numerator minus log the denominator. So if you do that, then you'll basically get this form back again. So from now on, we're going to look at this equation in the red square. Okay? This is the KL divergence equation. Now, one thing to realize that it's never negative and only 0 when the two distributions are exactly equal to each other. Okay, so how does that happen? When these two distributions are equal, so you can cancel them out, and you'll end up with 1. So logarithm of 1 is just 0, and that's why you get a loss of 0. So how do you get the loss of 0? When the two distributions are exactly equal to each other. Okay, so the two distributions here is y and y hat. These are the two distributions. Now, if we take a very simple example, then let's say we have two different distributions. Both of them are from the uniform distribution, and each one of them has these probabilities. So we're going to apply the KL divergence. We're going to take the first probability from the first distribution, which is 0.5, and then we're going to multiply it with logarithm of the probability from this distribution, which is 0.5, divided by the probability from this distribution, which is 3 over 4. Okay, so you have 0.5 times logarithm 0.5 over 0.75. And then we're going to do it for the second probability. So basically we have again 0.5 times 0.5 divided by 0.25. Okay, and if you add these up together, then you'll get 0.06. That means the KL divergence gives a value of 0.06, that means these two distributions are somehow similar to each other. Now, in deep learning, you'll basically see the KL divergence. One major use of the KL divergence is in variational autoencoders. And we're going to talk about autoencoders and variational autoencoders later on in this course. Okay, so when we reach to this variational autoencoders, you'll see how the KL divergence is utilized. Now I have a question for you. Is KL divergence same as cross entropy for image classification? And the answer is yes, it is. Because if you look at this equation right here, then basically in image classification, we're using one-hot encoding for our labels. Okay, as we said in the cross entropy lecture. So therefore, when yi is the actual label, it equals 1. So basically, you'll have log 1 over 1. Okay, so 1 over 1 is just 1, so log 1 is 0. Basically, you'd end up canceling this whole term out. And when yi is not the correct label, then it equals to 0. So you're multiplying 0 with this log 1 over yi. You're multiplying this log 1 over 1i with 0, so you're also canceling this term out. So in both cases, if it's the correct class or not the correct class, you're basically canceling this whole term out, so you'd end up with only the cross entropy term. So KL divergence equals to the cross entropy term in image classification problems, because the entropy term is removed. Okay, so that's it for KL divergence. I'll see you in the next lecture. Thank you very much.